help you tonight. Probability and statistics is not my strong suit.
Okay.
It's kind of, it's a branch of discrete mathematics that tends to be a little separate from the others. You know, a lot of people will take that class, probability and statistics. I've never ever tutored anybody taking that course. Most of the probability and statistics stuff that I deal with is the stuff they teach algebra 2 and a little pre-calculus, but I'm not that familiar with a lot of what they're talking about here. So
Okay.
I'm willing to do the best I can to help you with it, but I'm not sure that I'm going to be able to. Is there a particular page you want to start with? What do they give you in the way of textbook for this stuff?
I have no textbook.
So it's just this printed material that they're giving you that
Yes.
kind of describes what's going on. All right, well, I read through here, and I think I get an idea of it. Although, okay, I know what expected value is. Although I've never seen it like this. When I say never, I mean since I've been tutoring. I'm sure that I covered all of this 40 years ago when I was in college, but to be honest with you, the only math I know is what I've been tutoring for the last 7 years.
Yeah.
That's the only math I remember. I mean, I've refreshed myself on that. So, you understood this table, okay?
Yes.
Okay. These are the odds of throwing one die, or rather, okay, so you can only get a 1 if you throw a 1 on each die and multiply them together. You get a 1, and that's 1 in 36. Is that, am I understanding it correctly?
Yes.
Okay. In other words, this number here is the product of your green and red cube.
Yes.
Okay. Oh, and this, the bottom line is the product times the white line, right?
Yes.
In other words, it's 2 times that number gives you this number. Yeah.
Yes.
6 times this number gives you this number. 5 times that number gives you this number. Okay. All right. The simple average of the list of products, is there something, we just add those up and divide by the number of them?
Yes.
Okay, well that's pretty straightforward. You can certainly do that. Is the expected value lower or higher than the simple average? Explain what's going on here.
So I think the expected value I am supposed to get from D.
No, you get the simple average from D.
No, the other D. There's 2 Ds. It's above the chart on the right-hand side.
Oh, okay. Yeah, so the expected value would be the sum of each of these things. Right? 136 plus 1/9. In other words, it says the sigma of x times p of x. Well, this is x times p of x. So we must add all of these up to get the expected value. So let's think about that for a second. This is going to be a simple average. And this expected value, how is it going to be lower or higher than this simple average? Any thoughts on that?
I would think lower.
Well, let me think about it for a second. Across the top is all of our possible products.
Right.
But the probability of each one of them is not the same. So when you take a simple average, you're assuming that the probability of each number coming up is going to be the same, right? Whereas when you take an expected value, you're multiplying the outcome, each of these numbers, by their respective weights. In other words, there's only 1/36 of a probability of having the product be 1, but it's much more likely to get a product of 5. So the 5 would be more heavily weighted than the 1. When you figure the expected value, you're basically weighting each of the possible outcomes by its probability. So let's see. In other words, there's a greater likelihood of coming up with these numbers. Bigger numbers have much higher x times p of x than the smaller numbers do. So I would expect the expected value to be higher than the simple average. When we take a simple average, we're weighting the 1 the same as the 36. When we do an expected value, we're going to weight the 36 much higher. There's a full, or x times p of x is 1 there. In fact, there's more ways to come up with 30 than anything else. So you can see that it's much more likely to come up with 30 or 36 than it is 1 or 2 by a lot. So the expected value takes that into consideration, basically, by summing each of them. And since it appears your bigger numbers are more heavily weighted, the expected value should end up on the big side of the simple average. And that's what's going on. I don't know if that's an adequate explanation or not.
No, I understand.
Okay. All right. This one has a probability distribution function. And my calculus books do cover this a little bit. And that's one of the harder things in calculus to understand, is using it with the probability distribution function. Now I'm a little confused here. X represents the amount of time a person waits in line in minutes, right?
Right.
So what is f of x?
The function?
Usually they tell you what f of x is. In other words, I would have thought that the time a person waits in line is a continuous random variable. It almost seems like they're saying the time a person's going to wait in line is going to be f of x, but not if x represents the amount of time a person waits in line in minutes. I don't quite understand what f of x is going to be.
I mean, I can send you the first page, which has definitions on them, if that helps.
Well, see their question first. And I'm not quite sure, although most people get service in a short time, a small fraction of people must wait in line a very long time. Well, if x is a very big number, I still can't quite figure out what f of x is going to be. I know they're calling it a probability distribution function, but
it says in the problem, like, f of x is 0 when x is less than 0.
Right. That
And
makes
f of
sense
x
because
equals...
x can't be less than 0 if it's the amount of time a person waits in line.
Right.
So, in other words, the only thing we really are concerned with, realistically, is this part of it. Explain why wait time is a continuous random variable and not a discrete random variable. Well, I guess the explanation for that would be a person can wait in line 2.5 minutes. It's continuous, or 2 minutes and 12 seconds. In other words, it's not required that x has to be in discrete increments of integers. That's the only thing I can think of. That seems rather simple. Make a labeled sketch of this function. Well, we should be able to do that, I think. Let's see how hard that can be to do. Well, let's see. To the left of 0, it's pretty easy. And to the right of 0, we have e to the minus 0.2x. So this minus is a reflection over the y-axis. Which means that instead of being e to the x like this, it's going to be like this. Which means that by the time it gets to there, it's going to be doing that. You with me so far?
Yes.
Furthermore, that 0.2 there is a vertical shrink factor. So it would take something that looks like this and make it look like that. That's what a vertical shrink on an exponential is going to do. And the 0.2 up here represents a horizontal stretch, which takes your exponential function and stretches it horizontally so that it would look something more like that. In other words, if you tug on the end of that string, and you get this. So we've got vertical scrunching, horizontal stretching. This thing should be almost a straight line. The only thing we know for sure is it goes through that point right there, which is 0, 1. In other words, when x is 0, f of x is 0.2. Correct? Yeah, e to the 0 is 1. So the first point on our graph is right there at 0, 0.2. And we know that as x goes to infinity, we're going to approach the asymptote like that. Presumably, this is f of x. I don't know what else it would be. That's x. So there's a labeled sketch of this function, best as I can tell. It's a piecewise function. It's actually open right here and closed. Yeah, I didn't draw this right. I drew it. Well, yeah, I drew it right as long as this is 0.2 on the f of x axis.
Right.
Okay. Well, I think that's right. Determine the total area under the curve by setting up an appropriate integral, calculating the integral value. Okay. Well, we're going to want to integrate from 0 to infinity. Have you had these kind of integrals yet?
No, I've only had, a little bit.
Let's see. These are called improper integrals. Whenever one of the limits of integration, improper as opposed to indefinite. In other words, you have definite integrals, you have indefinite integrals, where there are no limits of integration. But then an improper integral is where one of the limits is infinity. And it can be either one. You can be going from negative infinity to infinity, or some number to infinity, or whatever. And the only function we need to integrate is this one. That's actually fairly integratable. Let's do it. If we integrate e to the 3x, we get e to the 3x divided by the derivative of the inside. Okay?
Right.
So
it'd be
go ahead.
0.2 e to the negative 0.2x divided by negative 0.2?
Yeah.
Yeah.
The 0.2's cancel. So the integral ends up being that. And then we're going to evaluate it from 0 to infinity. Now, most of the textbooks I have insist that you substitute b for infinity, and then you take the limit as b goes to infinity. But I've never found a problem with just substituting infinity for this. In other words, our answer is going to be minus e to the minus infinity,
Right.
minus e to the 0. Well, minus e to the minus infinity goes to 0, as that's what the limit would be. In other words, most things are going to have you do it this way. They're going to take the limit of minus e to the minus b as b goes to infinity. Well, we can see that that's 0, right? In other words, the limit of that thing is going to go to 0. It's 1 over e to the infinity. So this goes to 0. This is 1. Negative e to the 0 power is 1.
So the answer would be negative 1?
Hold on, maybe. Either negative 1 or positive 1. No, this is negative 1. Because that 0 is not acting on the negative sign. That exponent right there is only acting on the e. So e to the 0 becomes 1, and then that negative sign is independent from it. So we're going to have a negative 1, so the area under that curve is 1.
Huh.
And it is finite, which is rather odd. When you look at this problem, and you realize that this line never reaches the x-axis. Even when x goes to infinity, it's barely above the x-axis. So it looks like that would be an infinite area under that curve. But not so. There's a lot of functions that look to be infinite, and they're actually finite. Have you ever heard the Gabriel's horn problem?
No.
This will blow your mind. I got to tell it to you just because you'll be fascinated by it.
Okay.
Take that function which is y equals 1 over x, the positive part of it. Rotate it about the x-axis, and you get what is called Gabriel's horn. You get a figure like that.
Huh.
Well, here's the kicker. The volume is finite, but the surface area is infinite. And there's a lot of things like this in calculus that are paradoxes. In other words, how can you have something that has finite volume and infinite area? But you can. And this is a perfect example of it, Gabriel's horn. And basically the reason is that when you find the volume of Gabriel's horn, you split it into disks, right? And the radius of each disk is this, but you square it because the volume of each of these disks is pi r squared. So when this thing gets squared, it's 1 over x squared. And when you do the math, this is finite. And yet, if you merely try to calculate the area under the curve as opposed to the volume, it's infinite when you do the math. If you figure out the area from 1 to infinity of this function, you get an infinite answer. And yet, the volume of Gabriel's horn is finite, or the volume's finite, the surface area is infinite. And what does that tell you is that if you fill Gabriel's horn with paint, you couldn't do it. It's a finite amount of volume, but an infinite surface area on the inside as well as the outside of Gabriel's horn. The inside of that horn is an infinite area. That's why I said it'll blow your mind. But anyway, let's get back to the other stuff. All right, so we did C. We figured out the total area. And that should have been a clue when we came up with minus 1. Can it be minus 1?
No.
No, you can't have an area under a curve be negative. That's a positive area there, if it doesn't go below the x-axis. In other words, that's all positive. So when I came up with minus 1 and we couldn't figure out whether it was minus 1 or plus 1, there's a clue. It's got to be positive. And it was anyway. I was doing the math wrong. I was assuming that minus e to the 0 power was 1. But that's not what this says. It's a negative e to the 0 power. In other words, if I want to put parentheses in here, I got to do it like this. The negative is not being taken to the 0 power. So we did come up with an area of 1, and I'm quite certain that that's the proper area. In fact, when you get into calculus, they come up with a new definition for natural log. You know what their definition is for a natural log function, if I can remember correctly? It is defined as, oh man, I'd have to look it up again, but it's defined in terms of the area under the curve. it means the area under the natural log function is 1 from 1 to infinity or something like that. But anyway, calculus comes up with a new definition based on area under the curve rather than the typical definition of natural log, which is, log base e, which is kind of interesting. But comment on the value you got in B.
I think it means C.
It must mean, because we didn't get a value in B. And what it tells us about this probability density function. Well, we came up with a value of 1 as the total area under the curve. So I would think that in terms of probability density function, it's 1. What does it tell us about the probability density function? Wow. I would need a sheet of paper that has definitions on it. Unfortunately, we don't have time to do that tonight. So I can't really help with that question there. Let's real quickly take a look at some of the other, or let's see, some of the other stuff you sent me. I think I know, these things like the normal CDF. That's a function you have on your calculator.
Yes.
That you can come up with that. And it must have 4 parts to it. The lower bound, upper bound, the mean, and the standard deviation.
Okay. Yes. Though, bell curve I can do just fine.
Okay. And you understand the bell curve about, let's see, the 3 key numbers on the bell curve are 66.6% of the curve. 66.6% of the area is going to be within 1 standard deviation. In other words, right here, that represents 68% of the area under that curve. It's not 66.6, it's 68, okay? 2 standard deviations represents 95% of the area, and 3 standard deviations represents 99 point, what, 6 or 5? What's the decimal after that? For 3 standard deviations, do you know?
I do not know.
68, 95, and 99 point something. I can't remember the point. That's interesting. This I did not know. That the 2 points of inflection are exactly 1 standard deviation away from the mean. So there's your inflection point right there and right there. And we can certainly see that it's concave down for most of that curve, and then it becomes concave up.
Right.
Match each expression to the shaded area. 2 have been done. So this matches this graph right here because I guess they don't put the 0 in it if the mean is 0. Why are there only 2 numbers in here? Shouldn't there? It looks like there should always be 4. There's 4 there. There's only 2 there also. So what happens if you only have 2 numbers? How do you interpret that?
Maybe it's assuming that like the numbers that don't have change have a standard deviation of like a mean of 0 and a... So
they just don't list the 0? In other words, we know what this is. This is the lowest value is 7, the highest value is 10, the mean is 10, and the standard deviation is 6, correct?
Right.
Okay. So which curve would that be? You know, I'm sorry about this, Diana, but I'm going to have to leave because I have a 6:30 scheduled tonight.
All right, that's fine.
Okay, so I'm sorry I couldn't be more helpful on this stuff, but hopefully you'll be able to use your information to figure it out. I would like to study probability and statistics a little bit more, but there's such little demand for people that need it. So I don't end up putting a lot of effort into it. But anyway, we can do 7 o'clock again next Thursday?
You mean 6 o'clock?
Is your standard, you changed it to 6 this week, didn't you? What, weren't we originally?
No, it's not.
Yeah, we were at 7 originally, and you made a new one at 6, and so I canceled the one that was at 7, just moved it to 6. I assume that's what you wanted me to do.
Oh, I thought it was normally at 6. Okay.
No, you're normally at 7.
Yeah,
in other words, I've got you locked up at the 7 to 7:30 spot.
Oh, okay, then we can have it at 7.
Okay, just leave it the same.
Yes.
Okay. Now,
sorry, it's just my tutoring program is finished, so I'm no longer coming home at 6.
Okay.
So it's a bit disorienting.
Okay. Well, I will talk to you
7
next Thursday unless otherwise notified.
All right.
Okay.
Thank you.
Bye-bye.
Bye.